Hello everyone, in this video I'll talk about the diffusion models for the task of image generation and more specifically the DDPM paper from the year 2020. And once we figure that out, I'll have to talk about another paper called DDIM for accelerating the inference time. And yeah, I hope you enjoy it, and without further ado, let's get started. DDPM is the first work of diffusion model in deep learning that came in 2020, and now it has more than 10,000 citations. In DDPM, once we have an input image, we can add a tiny bit of noise and do it again, and again, and again, and again, till we reach this noisy image that doesn't look like the original image much. And we call this procedure of adding noise the forward diffusion. And mathematically speaking, each of these images can be considered as marginal distribution, and we can use the term Q as the procedure of adding noise. This procedure can be denoted as a multiplication of multiple noising procedures that each should add noise to change our state from xt-1 to xt. And to visually understand this formula, we use the first noising procedure that we can reach marginal distribution x1 given x0. And then we can reach x2 given x1, and we can do it over and over until we reach x5, which is the capital T in the formula. And the next question would be how we can mathematically denote each of these noising procedures that makes us reach xt given xt-1. Formula used shows that we can represent xt by some random normal distribution, that the mean is xt-1 image at the previous state multiplied by a coefficient, and this coefficient has alpha t on the numerator, which is a hyperparameter unique per each time step, and alpha t-1 on the denominator, that is again a hyperparameter, but for the previous time step. But note that all these hyperparameters should be a value between 0 and 1. You can kind of assume that alpha 0 would be 1, and as we go over and over, we decrease it so that alpha t is less than alpha t-1. So that means that numerator should be smaller than the previous state on the denominator, and the whole fraction should be a value between 0 and 1. So the coefficient is less than 1, and we multiply the pixel values in previous time step by a value less than 1, and we kind of make the values closer to 0. And one thing to note is that we desire to reach a random normal distribution at the end that has 0 mean and unit variance. And at the end, if I use the alpha capital T to be 0, that means the numerator is 0, so the coefficient is 0, and also the mean of this normal distribution is 0. And we can say the same thing for the variance. It is multiplied by coefficients that initially the fraction should be closer to 1, so we have no variance, and the denoised image is equal to a normal distribution that the mean is the same as the image and the variance is 0, and we iteratively add noise by decreasing the value of this fraction, and ultimately the fraction becomes 0, and we have a random normal distribution with 0 mean and unit variance. But interestingly, in the paper they show that we can have a single formula that instead of iteratively adding noise, we can directly go to any xt given the denoised x0 by defining this normal distribution. And visually speaking, that means I can directly go from x0 to x5 or any other noisy image without iteratively using the formula and wasting my compute resources. But this formula of denoting xt by a normal distribution is not straightforward to implement, so they use something called a reparameterization trick, and we can denote the same formula this way. And this way, we can start from x0, multiply by a coefficient that is a value between 0 and 1, so it has to make the x0 smaller, and then we sample epsilon from a random distribution with 0 mean and unit variance, and we add this noise, but first by multiplying it by a coefficient. And as I told you before, this alpha t is a hyperparameter coming from a scheduler that we are decreasing it over time. And then finally we get xt, that is a noisy image that we desire. And believe it or not, this is the only formula that you need to know from the forward diffusion. That how we can achieve any xt, which is some noisy image in the middle, given the denoised image x0. And the next thing to talk about is the backward diffusion. That is the only thing you're going to see at inference time. Backward diffusion can be denoted this way, that the denoising procedure is P now instead of Q that we used for the forward diffusion. And for defining it, we start at Px capital T, that is the most noisy image that is coming from a random normal distribution with zero mean and unit variance. And essentially that means at inference time, you have to sample a random noisy image. And then we have x5 in our case, and we iteratively multiplying it by this denoising procedure. Like we reach x4 given x5, and then x3 given x4, and then we do it over and over until we reach the original denoised image. And based on this formula, xt minus 1 is coming from a random normal distribution in which the mean and variance are both coming from a neural network with parameters theta. And there are some heavy math behind it that I don't go through, but if you follow the math, you can see that instead of outputting the mean and variance, we can let the model learn the actual noise from the zero mean and unit variance that we sampled from and use to predict that instead of this mean and variance. And in case if we do that, then we have a simple training like this. In the training, at first we have x0, that is the original image without noise. Then we randomly sample a time step t from 1 to capital T, that is the whole time step. And for example, capital T could be a value like 1000, and then you sample this small t to be a value between 1 and 1000, and that can be used later in forward diffusion to add noise, and then we can reach xt given the original x0. But for doing it, we randomly sample a noise from normal distribution that has zero mean and unit variance. Recall the reparameterization trick that I told you before. And then based on this formula, that is the only formula that I told you you need to know from the forward diffusion, we can add noise to our original image x0 and derive our noisy image xt. But note that this noise that we add has a coefficient that relies on a hyperparameter alpha t that is unique per each time step. So our neural network epsilon theta should receive the noisy image xt that came from the forward diffusion, in addition to time step t that should give some sort of signal to our model that, okay, I'm at step t, so you should learn how much noise you should predict to remove from this xt to drive xt minus 1. But note that we don't care how big the noise is, because this square root of 1 minus alpha t is a known value, and what is unknown to us is this epsilon value. So we penalize the model in loss function to predict the actual noise from random normal with zero mean and unit variance that we sampled, and it doesn't really need to care the intensity of the noise because the intensity is a known value, and based on the t that we give it as additional signal of the input, it needs to kind of learn by itself that what is the intensity. And by repeating this procedure over and over, we can train our denoiser that at each time step it should predict the noise and denoise it for us. So basically our denoiser neural network is the same function p that I showed you before in the backward diffusion. And at inference time, we have the sampling algorithm that we start by sampling x capital T from random normal distribution with a zero mean and unit variance, and we want to iteratively denoise it using our neural network to reach the denoised image x0 at the end. So we have a for loop to iteratively denoise the noisy image. For denoising it, let's forget this z for now, and remember I told you in the forward diffusion that we can denote xt by this formula that we reduce the mean xt minus 1 and we add noise. Well, you can try it yourself and use the reparameterization trick that I told you before, and by moving xt minus 1 to the left side of the equation, you can derive this formula that is exactly what's used during the noising procedure. But we have a neural network that predicts the noise that is added, and we just remove that noise to derive xt minus 1. But what is this z that we also need to add this to the formula? Let's understand it by visualization. In our visualization, let's denote x capital T, our random normal distribution, by this curve. And our denoised image distribution by this curve, there's a distribution of having all the images of cats and dogs, for example. And we sample from x capital T, that means we select a point like this one, And if we don't use the variable z in sampling algorithm, that means we have a straight line that goes directly to an image that can be a cat. But in our image generation pipeline, we also want to include variations. Well, for sure, I can start from a different point in X capital T to generate different image, but what if I want to also generate a different image, but from the same point? And that's where the Z comes. Looking at the formula, you can see that Z is also a random noise that we add at each denoising step. And that means one time it generates this cat, and the other time it generates this cat, but it also has the possibility to go in another direction and generate a dog image. But note that at our last denoising step, we want to reach the denoised image x0, so we set the z to be 0 because we don't want to have noises for our final denoised image. And it kind of makes sense, right? And yeah, that's all you need to know about DDPM, but there is some kind of an issue. That assuming x0 is the denoised image and xt is the noisy image, we can use our diffusion model to denoise the image in multiple steps and reach x0. But the issue is that there isn't a single path that can go from xt to x0. And that's where the DDIM paper comes to propose a new perspective for the diffusion process. Unlike DDPM that was using a Markovian chain for adding noise and denoising the image, DDIM proposes using a non-Markovian chain at inference time. But don't freak out, it is way easier than expected if I visually explain it to you. Assuming that we have our original image as x0, then this q of x capital T given x0 means that we can add noise in a single step using this formula that I showed you in DDPM to construct the noisy image. But then it proposes a non-Markovian process here that we can achieve any marginal distribution in the middle given xt, that is one step more noisy, and x0, that is the original image. And to visually see what I mean, we can achieve xt minus 1 given xt and x0. And likewise, we can achieve xt minus 2 given xt minus 1 and x0. And we can do it until we get all the marginals. But now you might wonder, okay, we have now a non-Markovian chain now that we can get everything in the middle given the original image and one step more noisy image. What's the point? Well, first let's understand how this Q can be mathematically represented, and then we can discuss it. Q sigma says we can derive xt minus 1 given xt, that is one step more noisier, and x0, that is the original image. The way we can derive it is by sampling from a normal distribution that the mean is coming from this formula. And surprise, surprise, this mean is exactly like the formula that we defined in the forward diffusion of DDPM, but with the difference that previously we had this noise sampled from a random normal distribution, and it could be anything. But now the noise is this term that relies on xt and x0. So in other words, we are not interested in any noise, and we want only the noise that we can use it to derive xt in the next step given the x0, and throughout the whole procedure we use a single noise. Another difference is that this sigma t that we have in the square root and the variance of the normal distribution. The role of this sigma t is to add stochasticity, and in fact if you put the value of 0 as sigma t, then the normal distribution has variance of 0, which means we can deterministically traverse every noisy image in the middle given the noisy image x capital T and x0. Okay, now knowing this non-Markovian process, how we can write forward and backward process in diffusion. For the forward process, it can be calculated using the Bayes rule, and xt is derived from xt minus 1, but now in addition to x0. And based on Bayes rule, we need this q xt minus 1 given xt and x0 that I just told you how it is calculated, and one step forward diffusion to derive xt given x0, and likewise deriving xt minus 1 given x0. And about the backward process, our neural network should estimate the q xt minus 1 given xt and x0, but since we don't have the x0 at inference time, we also estimate it using our neural network. But you might say our neural network only predicts noise, and you are right, but once we are having this noise, we can reach x0 from xt in a single step. So intuitively, our neural network at each time step t should have an estimate of ultimate x0, possibly with large errors as the task is challenging, and then it returns back to xt minus 1 and denoises it again, but this time, since the xt minus 1 we have less noise, the task for neural network should be easier to predict the noise. Hopefully it seems fine, but there's one thing that I missed, that when we reach time step 1, we can directly estimate x0 in a single step, and we don't really need this non-Markovian process anymore. And to sum up, the sampling process is something like this, that if we want to derive xt minus 1 from xt at inference time, our neural network first predicts the noise, and when you use it to derive x0 directly from xt, possibly it has a lot of errors, and then we use the same predicted noise to add some more noise to x0, but now with less severity to reach xt minus 1. And optionally, to add more diversity in our denoising step, we can add the stochasticity using the random noise. And the loss of DDIM should be this formula, that the model prediction P of theta should resemble the non-Markovian Q that we defined earlier in this formula. And remember from DDPM that our neural network has the job that it has to start from x capital T and then denoise it step by step. And simply substituting them in the formula and then taking their log to turn the multiplication into addition, we have this term as our loss function. But notably in the paper, they show that this loss is equivalent of what's used in DDPM, and therefore we don't really need to train our diffusion model using DDIM. We can train it using the DDPM, that is kind of easier, and those should be the same. So now you might wonder, okay, if they're achieving the same thing, what's the point of using DDIM? The point is that at inference, we can use less than t steps to accelerate the inference time. Like we can train it in 1,000 steps, but at inference time, we use something like 50 steps. And just to visually show you how, let's revisit the sampling formula. At inference, we start at step 999, that is a random Gaussian noise with zero mean and unit variance, and then we predict S0 using a single step. That is quite garbage, as you see. And then we add noise with less intensity to reach some steps in the middle, not necessarily one step earlier, but a huge jump to 781. And once we have this noise at 781, we can denoise it back to x0 using a single step. But now, since at step 781, I had less noise than at step 999, it is easier for the model to denoise. So at step 0, I have some image that is having kind of a higher quality compared to what I had earlier. And I repeat this again, like at the step 0, I used the second formula to drive step 581, and then having this 581 as the input, I can directly go back and predict the step 0. And now, as you see, we have something that has more quality, and then we can do it again and reach something better, and do it again, and finally we reach this high quality image of a Persian rock. And yeah, that was all I wanted you to know about the diffusion models. I hope you found it useful, and if you have enjoyed it, don't forget to like and subscribe. And until the next video, goodbye.